Here we're going to add head-to-tail vectors, but this time by the method of applying the laws of sines and cosines. This example demonstrates this method. A car travels 20 kilometers due north and then 35 kilometers in a direction 60 degrees west of north. Find the magnitude and direction of the car's resultant displacement. First of all, to draw the head-to-tail vectors, let's start with the vector A, which has a magnitude of 20 kilometers, and then draw this vector due north. Next, we'll follow this vector by another vector of 35 kilometers with the direction 60 degrees west of north. Now, by drawing the two vectors, the resultant can be drawn from the tail of the first vector up to the head, and then we can determine the magnitude and direction of this vector. Before we determine the magnitude and direction of the resultant, let us review the information given in this example. We have here the magnitude of the vector A, which represents one side of the triangle, and the other side of the triangle, which is 35 kilometers for the vector B. In addition to that, the angle of the vector B with respect to the positive y-axis is given as 60 degrees. And here we want to determine the third side of the triangle, R, which represents the magnitude of our vector, of the resultant vector. We apply the cosine law for R, where the values here of A and B are given, but the value of theta is not. To determine theta, we just subtract 180 degrees minus 60 degrees. That is 120 degrees. Substitute all the values of A, B, and theta into the cosine law, and the magnitude of 48.2 kilometers for the resultant is obtained. To determine the direction of the resultant, we use the sine law in order to find the angle beta. Here, sine beta divided by the magnitude of the opposite side to the angle beta, that is B, must equal to sine theta divided by the opposite side to the angle theta, that is R. Substituting the values of B, R, and theta, the magnitude of 38.9 degrees for the angle beta is obtained with respect to the direction of the vector A, and that is west of north. Adding the latter angle to 90 degrees, the angle of the resultant theta R with respect to the positive x-axis in the counterclockwise direction is obtained as 128.9 degrees. Alternatively, the example solved in the cosine and sine law can be solved by the component method. To do that, move the vector B towards the origin. So the information used before, 20 for the magnitude of vector A and 35 for the magnitude B, can be used here. In addition to the angle with respect to the positive x-axis of the vector B can be obtained by adding 90 to 60 degrees. That is 150 degrees. Doing that and following the same method we have done before, we get the magnitude of the vector 48.2 kilometers and the direction the same as we did in the previous example. To test our understanding to the additional vectors, Let's ask this objective question. Let vector A point from the origin into the second quadrant of the xy plane, and the vector B point from the origin into the fourth quadrant. The vector B minus A must be in which quadrant? Is it the first quadrant, or the second, or the third, or the fourth? Or answers B and D are both possible? Well, the answer obviously the fourth.